We will now conduct lab 5 AC network theorem, where we will verify Thevenin's theorem. To perform this experiment, we will need one 1K resistor, one 1.2K resistor, and one 2.2K resistor, and a capacitor of 0.1 microfarad. So the original circuit that we are considering is this circuit B.1, where there is a source of 3-volt peak and 1 kilohertz, and the circuit consists of one 2.2K resistor and a 0.1 microfarad capacitor, and the load of this circuit is 1 kilo ohm. So from verification of Thevenin's theorem, we will show that this original circuit and this Thevenin's equivalent circuit supply the same amount of current and power to the load resistance of 1K. So to perform this experiment, first we will have to determine the voltage across the load RL, which we will do by connecting the circuit and taking the voltage of node C, and then we'll have to find the Thevenin's equivalent voltage by removing the load resistor and taking the open circuit voltage across node C, which is shown here in figure B3. The load has been removed and an oscilloscope has been connected to node C, by which we will measure the Thevenin's equivalent. And then we'll need to find the Thevenin equivalent impedance, which we will do by implementing this circuit shown in figure B.4. What we'll do is, in our textbook, the source is turned off, and from the original circuit the source is turned off and replaced with a wire representing a short circuit. However, the function generator we are using is not an ideal function generator, so there is a presence of some internal resistance, which is replaced by this 3 ohm resistor. This 3 ohm resistor is the internal resistance of the function generator. And what we will do is, we could measure the Thevenin equivalent impedance by using an impedance meter in this open circuit area after the load is removed. But in the absence of an impedance meter, we can what we can do is, we can put a power supply here and calculate the voltage and current in this region. That is, if we find the voltage and if we find the current that is being supplied by this source, then by Ohm's law we can find the impedance. So that is what we'll be doing here. This source will create the current and that is drawn by the impedance, equivalent impedance of this circuit, and if we find that current, we can find the impedance by Ohm's law. The entire procedure for performing this experiment has been described in the manual, and we will proceed step by step and verify Thevenin's theorem. So first what we have to do is, we will have to construct this circuit, and as always, before constructing the circuit, we will measure the practical values of the resistances and capacitances that we are using and record them in the table provided. After that, we will start constructing the circuit. So on our breadboard, we will attach the resistances one by one and measure the resistance, and we will record them accordingly. Here I have attached a resistance. Now I will measure its practical value using a DMM. To measure a value using DMM, as always, we would need to place this knob in the resistance measurement mode and then attach the probes parallel to the resistance. we see that this is 0.971 kilo ohm. So this is the load of our circuit. The load resistance is 0.971 ohm, and we will record it in the table. Okay, then we'll remove this resistor and attach another resistor and measure its value. So again we'll use the TMM in the resistance measurement mode. We see that this is 1.187 kilo ohm. This is the value. This is the practical value of resistance R1, which was 1.2 kilo ohm according to the circuit. .187. Okay. Finally, this resistance, which is our 2.2k resistance, we'll be measuring its value again using TMM. We find that the practical value is 2.16 kilo ohm. Now we'll measure the practical value of the capacitance of our circuit, which is 0.1 microfarad. We will measure the practical value of this capacitor using an LCR meter. I place the measurement knob to 2 microfarad and then turn on the LCR meter. We see that there is a slight deviation from 0, but we can try to fix this by adjusting this calibrator. Okay, so you see that our LCR meter has been calibrated to 0. Now we'll place the capacitor in this measurement node. So we see that this is 0.092 microfarad. We'll record this value in our table. Microfarad. Okay, so now we're ready to construct our circuit. So we will now construct this circuit where we will attach this 1.2k resistance, create this node B by placing 2.2k resistance and 0.1 microfarad capacitance in the same node, and we'll place the load resistance of 1k in node C, and we'll connect the source between this node A and this ground node 0. So we'll do that now. First I am placing the 1.2k resistance. So I have placed the 1.2k resistance, and now I'll place the 2.2k resistance in this node. So I've placed 2.2k resistance in this node where there is one leg of 1.2k and one leg of 2.2k. Now we'll place the capacitor. One leg of the capacitor will be connected to this same node. So we have now connected 1.2k, 2.2k and the 0.1 microfarad capacitor. So we have essentially created this node B. Now we will connect this load resistance in this node C. So I am placing one leg of the load here and the other leg of the resistance here. So one leg of the load is connected to node C as seen in the circuit, and another leg of the load is connected to the ground node, node 0. So here this is node A, this is node B, this is node C, and this is node 0. We will connect the source between this node A, where we will place the red terminal, and this node 0, the ground, where we will place the black terminal. So I am placing the red terminal of the function generator, the source, in this node A, and the black terminal to this node 0, the black wire to this node 0. So now our circuit is complete. Now we will need to attach the probes of the oscilloscope, and we will attach it to the circuit right now. This is the probe of channel 1 of the oscilloscope. As always, we will place this black wire to the ground node and place this positive part of the probe to one of the nodes. So I'll place the black wire in the ground node, and since we'll have to calibrate the source to our required 3 volt peak voltage, I'll attach channel 1 to node A. So I've attached channel 1 of the oscilloscope to node A. And as I described earlier, to conduct this experiment, first we'll have to measure the voltage of the load, which is the load voltage drop. So we'll need to measure it by placing the oscilloscope, one of the channels of the oscilloscope, in node C. So I'll be placing the channel 2 probe in node C. So this is the channel 2 probe, and I'll attach the black wire to the ground as always. And attach the positive part of the channel to this node C. So now our circuit is complete, and we have attached both channel 1 and channel 2 of the oscilloscope with our circuit. So from channel 1 we'll calibrate the source to our required 3 volt peak voltage, and from channel C we will get the voltage drop across the load resistance RL. So after completing the circuit, now we move on to the function generator and to the oscilloscope, where we will take the reading. So firstly, I turn on the function generator by pressing the power button, and we see that by default 1 kilohertz frequency is produced as output, so we don't need to adjust it, as we need 1 kilohertz. And as always, the default signal generated is triangular wave. We produce sinusoid by pressing this sinusoidal button. So by pressing the sinusoidal button, we create sinusoidal output. So to adjust the amplitude, we will need to move on to the oscilloscope. So I turn on the oscilloscope by pressing the power button, which is located on top of the oscilloscope. The oscilloscope is powering up. And the default setting, which is stored from previous use, has produced this output. So we'll need to adjust this output so that we can see the signal clearly in our screen. So first of all, we need to adjust the time division. We will adjust the time division by rotating this horizontal knob, and we will change the time division so that multiple cycles of the waveform are visible in the screen. Now we can adjust the voltage divisions of channel 1 and channel 2 to adjust the amplitude within the screen. So I rotate this knob to reduce the to increase the volts per division of channel 1, and I rotate this knob to increase the volt per division of channel 2. So although it seems that channel 1 and channel 2 signal is of the same magnitude, however this is not true. You see that the voltage division of channel 1 is 5 volt per division, and that of channel 2 is 1 volt per division. So these two signals are not same in magnitude. If we increase the volts per division of channel 2 to 5 volts per division, now we can comment on the magnitude of these two waveforms. So we see that the magnitude of channel 2 is smaller than the magnitude of signal in channel 1. Okay. So from our circuit, we know that we have connected channel 1 to the source and channel 2 to the load. So first of all, we'll have to adjust the peak voltage of channel 1. So our required source voltage is 3 volt peak, which is 3 volt max. So we'll have to adjust the amplitude until we find 3 volt max in channel 1. So we will do that by adjusting the amplitude. By adjusting the amplitude, reducing the amplitude, okay. So now we see that the channel 1 Vmax is 3 volt, which is 3 volt peak. So we have calibrated our source to 3 volt peak and 1 kilohertz. So now we see that since the waveform size is reduced, we can decrease the volt per division so that the waveform is a bit clearer. Okay, so we see that our channel 1 Vmax is 3.04 volt, so the source peak voltage is 3.04 volt, and in channel 2 we see that the peak voltage is 680 millivolt. When the output is in millivolt range, we could increase the accuracy of this measurement by increasing the signal waveform to cover the entire screen, that is by decreasing the volt per division. So if we decrease the volt per division of channel 2, the signal will get larger. Okay, so this is the maximum signal coverage that we'll get. So this is the channel 2 waveform, which has been calibrated to fit the screen. Now we see that the channel 2 Vmax is 592 millivolt, but previously when the signal was in this form, the value was 680 millivolt. So if we decrease the volts per division and ensure that the signal is covering the maximum portion of the screen, the calculation within the system, digital oscilloscope system, will be much more accurate. So now we see that the value is 592 millivolt, and we should record this value in our table. So we found that the peak voltage of the load is 592 millivolts, and we are yet to determine the phase. Additionally, to make the phase measurement, we can use the cursor, but there is also a built-in function for phase measurement which we will utilize now. If I want to bring the phase measurement readings in this box, I'll press this box, and the phase measurement can be found in the delay category. So if I press this category, you will find that the source is channel 1 to channel 2, which means that the phase of channel 2 with respect to channel 1. So this is the phase. There are other types of readings, delay readings, that can be brought about by changing the type. So now we see that the phase is 27.6 degree. So there is a fluctuation between 27 and 28, so but the average is around 27.6 degree, and we will record that. So we have recorded the phase to be 27.6 degree. So for the next part of the circuit, for the next part of the experiment, we will have to remove this load resistance, and we will have to measure the open circuit voltage, which is the Thevenin equivalent voltage. So since our circuit is already connected in this B.1 configuration, if we just remove the load resistance, we will be getting to this configuration, because we have already attached the oscilloscope to our circuit. So by simply removing the load resistance, which is this one, if we take this out, we will be able to figure out and calculate the Thevenin equivalent voltage from the oscilloscope. So this is the Thevenin equivalent voltage is shown in channel 2. The signal has gone out of the screen, so we will need to increase the volt per division of channel 2 to bring it into scope. So this is the channel 2 is the Thevenin equivalent voltage. We see that the value of this voltage is 2.48 volt. So this is the Thevenin equivalent voltage. We also see that the phase is 36.3 degrees, and the voltage is 36.3 degree lagging. Also we saw in the load voltage that the voltage is lagging. So this is 36.3 degree. Okay, there is some fluctuation, but let's take it to be 36.3 degree on average. So in the table, we will be recording this Thevenin equivalent voltage in E Thevenin measured. So we measured the value to be 2.48 volts, and the angle is minus 36.3 degree. Also previously the angle was lagging, so it's minus 27.3 6 degrees. So this is our measured Thevenin voltage. After determining the load voltage and the Thevenin equivalent voltage from this configuration and this configuration, now we have to measure the Thevenin equivalent impedance Z Thevenin by constructing the circuit in this configuration. So it's not necessarily constructing, we will be simply modifying the original circuit so that we get to this configuration. We will be doing that now. So first of all, I am removing the oscilloscope and the source from our circuit. So after removing the oscilloscope and source, we have this configuration. So we have this T sort of construction where we have 1.2K, 2.2K and 0.1 microfarad. Then we will need to attach a 3 ohm resistance as RS. Notice that I am not measuring the practical value of the 3 ohm resistor, because since we're calculating the Thevenin equivalent impedance of this entire circuit network, our calculation will give the practical value of this 3 ohm resistance, so we don't need to calculate it separately. So now we'll need to attach this 100 ohm resistance. So we need to measure the value of this 100 ohm resistance practically. So I'll attach this 100 ohm resistance in a remote part of the breadboard disconnected from our original circuit and measure its practical value. And as always, we'll use the DMM in the resistance measurement mode. So the practical value of our resistance is 96.8 ohm. We need to record it in our table. We will need to use this value later for our calculation. So 96.8 ohms. So the practical value of this R3 is 96.8 ohms. For the calculation of Z Thevenin, a box has been given for the required calculations. So we'll record the value of R3, 96.8 ohms in this region. And now we'll attach this resistance to our circuit. So we place this resistance between this node C and this this node which is attached to the ground. So now our component placement is complete. We will now attach this function generator to create this source. As shown in our circuit diagram, we'll place the red wire, the plus end, in this node S. And we will attach this negative polarity, the black wire, in this ground node. The voltage parameters for this source is 1 kilohertz and 3 volt peak. We already adjusted our function generator to this value for the original circuit configuration. So but still we will need to check if our source is producing this value. First of all, let's connect the channels of our oscilloscope to the circuit, and then we'll move on to the calculations. As always, we'll be attaching channel 1, the black probe, the black polarity or black wire of the channel 1 to the ground, and the positive part of the probe to this node S. For channel 2, from the circuit diagram, we see that this resistance, 100 ohm resistance, this is actually a sense resistor. We'll use this sense resistor to calculate the current IS2 that is supplied by the source. So we'll attach this channel 2 of our oscilloscope to this node C, so that we can calculate the voltage drop of this resistance and then calculate the current IS2. As always, the negative or black portion of the oscilloscope is attached to the ground, and the positive end is attached to this node C. After attaching our oscilloscope to the required nodes, we see that the oscilloscope is displaying these waveforms. We verify that our source is already supplying 1 kilohertz from the display in the function generator, and from the oscilloscope measurement, we see that the channel 1 Vmax is 3.04 volt. So our supplied voltage is 3.04 volt max or peak and 1 kilohertz, which is as stated in our circuit diagram. So from channel 2, we'll measure the voltage drop across the sense resistor, and we'll also calculate the phase. As I mentioned earlier, if the voltage is low, we should increase the time division this is the maximum utilization of the screen that we'll get for channel 2. So we'll record the values in this position and then continue with our calculation. So first of all, we see that the channel 2 Vmax is 98 millivolt, and we will calculate the phase by using cursor, not through this calculation, so to get the most accurate reading possible. So VR3 is 98 millivolt, and we are yet to determine the phase angle theta. So from initial observation, we see that the source, which is displayed by channel 1, the yellow signal, is lagging, and our voltage drop across the resistor is leading. So the signal, the sign of the phase will be plus. We record the sign of the signal plus over here. From the cursor, we will measure the delay delta t, and then we will calculate the phase theta. So we'll use the cursor to measure the delay delta t, and from there we will calculate theta. So we turn on the cursor and change the mode to manual, and we change the type to time, since we will be measuring the time delay. We place one of the cursor A, to the peak of this channel 2 waveform, and cursor B to the peak of this waveform. Slight adjustment is required. Okay. So after slight adjustment and placing the cursor in the peak of channel 1 and channel 2, we see that the time difference is 30 microsecond. We'll record it in our calculations. So delta t is 30 microsecond, and we'll use this to calculate our phase. So 30 microsecond into 1 kilohertz into 360. Using our calculator, we will calculate the value 30 microsecond into 1 kilohertz into 360 degree. So 10.8 degree plus, so plus 10.8 degree is our phase. So our VR3 is 98 plus 10.8 degree millivolt. So this is our VR3. So from our circuit, we saw that we need to measure this current IS2. So from the circuit, we can say that IS2 is equals to VR3 over R3. So we will measure this current IS2 by using the formula VR3 over R3. So VR3 is 98 angle 10.8 degree, and the value of R3 is 96.8, the practical value that we measured earlier. So we know that the current is VR3 by R3, and VR3 is 98 plus 10.8 millivolt, so it's 98 angle 10.8 millivolt divided by 96.8. To calculate the current, we use our calculator. 98 into 10 to the power minus 3, since it's millivolt, angle 10.8 divided by 96.8. We see that the answer is given in rectangular form. Let's convert it to polar form. So our current IS2 is 1.0123 into 10 to the power minus 3, angle 10.8. So it's 1.012 angle 10.8 milliamps, since it's 10 to the power minus 3. So that is our IS2. We know that our source VS2 is 3 volt peak, 1 kilohertz and 0 degree. So VS2 is 3 angle 0 degree. So our Z Thevenin would be VS2 by IS2. So it's 3 divided by so So our Z Thevenin is 2964.42 angle minus 10.8. So from this Z Thevenin we will have to find R Thevenin and C Thevenin. So we have to convert this to rectangular form. So it's 2911.91 minus 555.478 ohms. So from here we know that RTH is 2911.91 ohms and XTH is so our reactance is 555.48 ohms. If we notice from our circuit that the only reactive component of our circuit is a capacitance, so the entire reactance is created by this capacitance. So we can say that XTH is equals to 1 by 2 pi FC TH. From here we will calculate the Thevenin equivalent capacitance. Right here. Two pi, frequency is 1 kilohertz and XTH is 555.48. It's 2.87 into 10 to the power minus 7 farad, which we can write as 0.287 microfarad. So this is our CTH. So RTH is 2911.91 ohms and CTH is 0.287 microfarad. Also we have to record our measured Thevenin Z Thevenin, the Thevenin impedance here. So we will write it as 2911.91 minus J 555.478. So this is our measured impedance and this is the theoretical value which I calculated earlier. So now our task is to implement this Thevenin equivalent circuit where we will input a Thevenin voltage as the source. R Thevenin and C Thevenin will be the Thevenin equivalent replacements, and we will put the load to be 1 kilo ohm, and then we will see what is the voltage drop across this resistance. this load. To construct this Thevenin resistance and the Thevenin capacitance, we will need to use variable resistors and capacitance box, or we can combine multiple resistances and capacitance to get to this value. So we can combine multiple resistances and capacitances to get this Thevenin equivalent resistance and this Thevenin equivalent capacitance. To create our required Thevenin of 2911.1 ohms, we use one 2.2k resistance, two 100 ohm resistance, one 10 ohm resistance, and one 3 ohm resistance. So we get 2200, 200, 10, and 3. So we use one 2.7k. So here we have 2700. So we have 2913 ohms. So if we place these resistances in series, we will be able to get the resistance we require. Similarly, to get the Thevenin equivalent capacitance of 0.287 microfarad, we will use two 0.1 microfarad capacitors and two 0.047 microfarad capacitors, which will give us a combined capacitance of 0.294 microfarad. That is the closest we can get. So after placing this, combining these resistances and capacitance, we will use our DMM and LCR meter to see actually what value of combined resistance and capacitance we get. Remember that for resistances, we can add the values by placing the resistances in series. For capacitance, we have to place the capacitors in parallel. By placing the capacitors in parallel, we will be adding the values. So let's construct our circuit. At this point, we should remove all of our previous connections. I'm placing the resistors in series. So we have placed all these resistances in series. If you look at the connection, this is we have connected the resistances in series. There is a little mistake here. If you look closely, I have connected these resistances in series. So if we attach our DMM, using our DMM, we find that we have a value of 3.02, around 3.4 kilo ohms. So let's try and remove 100 ohm from here. So we find that the equivalent is around 2.85. So maybe attaching a 50 ohm would give us a better approximation. Okay, so I've attached to 22 ohms. So two more should do the trick. No. Okay, so we are close enough. We have a practical resistance of around 2.91. Okay, 2.908. So we have a R Thevenin of so practically we have implemented 2908 kilo ohms, which is very close to our calculation. We have implemented this and we needed this, so we are very close. Although we calculated this approximation, but due to the tolerance or error in the practical value, we used a separate set of resistances, but in combination we got this. Now let's go for the capacitance. So we'll attach the capacitance in parallel. We're attaching the capacitances in parallel. when we add capacitances in parallel, we add the capacitance values. So we have combined in parallel. So now we will use our LCR meter to find the capacitance value. So I'll attach some wires to this crocodile clip so that I can take the reading from the board. .256. So we need a bit more to reach the required 0.28. Okay, so we have 0.304, which is very close to what we have, 0.294. So we're good enough. We wanted 0.287 microfarad, but we have 0.303 microfarad, which is close enough. So now, according to our circuit, we have to build this circuit where we place this Thevenin equivalent resistance and Thevenin equivalent capacitance in series with the load, and then we'll use the Thevenin voltage as the source and we'll find the load voltage here. So we have already placed the combination of capacitance and resistance here. So we will make this entire resistance branch series with this capacitance branch. So I'll just attach this end in series with this capacitance branch. So this will be connected in series with this. So I use a wire to connect this in series. Now I'll need to place the load of 1K which we removed earlier and place it in series with this capacitance, which we'll do by placing the resistance here and here. So we have completed our circuit. This is the Thevenin equivalent resistance, Thevenin equivalent capacitance, and this is the load. We should now attach the function generator, and we will attach the function generator by placing this red probe and black probe to our circuit. So we'll place the red probe to the end connected to the Thevenin equivalent resistance and the black probe to the other end of the load. So we have connected the circuit. Now the input frequency was 1 kilohertz, the same frequency will be for Thevenin equivalent voltage, but the value of the Thevenin equivalent voltage is 2.48 volt. So we will use 2.48 volt as the input voltage. We don't have any control over phase, so we will just place the amplitude, calibrate the amplitude to 2.48 or close to 2.48 volts. We'll attach the we'll attach our oscilloscope. I'll attach channel 1 to the source. The black probe always goes to the ground, and channel 2 parallel to the load to get the load voltage. To get the load voltage, I place the oscilloscope probe at this node. Okay, so now we're ready to get the readings. So our frequency is 1 kilohertz as before, and now we move on to our oscilloscope. We see that channel 2 has gone out of the scope, so we adjust the vertical settings. Now if we go to measure, we see that channel 1 voltage max is 3.04 volt. We need to set it to 2.48 volt, which we measured as the Thevenin voltage. So let's adjust the amplitude and get as close to 2.48 volt as possible. So channel 1 max, which is connected to our source, should be 2.48 volt max. Okay, so we have set 2.48 volt max in channel 1, which is our source, and we do not have any control over the phase of the input, so we are just setting the input voltage. So we see from channel 2 reading, channel 2 Vmax, that the value is 592 millivolt. This is our V load of Thevenin circuit. We should record this in our table. So we have measured the V load of the Thevenin circuit to be 592 millivolt. We are not measuring the phase angle because we could not set the required minus 36.3 degree phase, which was the Thevenin voltage, so we will not get the desired angle of the output. But we see that we have the same magnitude of the voltage in both the original circuit and in the Thevenin equivalent circuit. Thereby we have proved Thevenin's theorem that this original circuit produces the same load voltage as this Thevenin equivalent circuit.